So for the second talk of this last session, we have Alona talking about the work of Olena on the limit theorems for the solutions to multipoint inhomogeneous boundary value problems with parameters in Sobolev spaces. Please.
Thank you for introducing me, and thank you all of you, special organizers, to give me this opportunity to present you some of my results. And today I present to Institute of Mathematics in Kyiv and in Prague. And also, I am not an expert in differential geometry, so be polite, but I hope that you will not sleep during this presentation, because actually I deal with ordinary differential equations and some methods of functional analysis. So the red line of this talk is to present you some results about character of solvability and continuity in a parameter. The most general classes of boundary value problems with parameter in Sobolev spaces. So firstly, we'll talk about some motivation moment. Then we formulate the statement of problem, and also we'll formulate the main results concerning continuity, the solution in a parameter. And the last one, we will formulate some theorem about approximation. So if we talk about differential equations, so the beginning must be from Cauchy problem. So the question about continuity in a parameter of solution to Cauchy problem were investigated by various mathematicians few centuries. It's normal. It's in concerning that fact that this type of problem in some sense generalize or used to and generalize well-known Bogoliubov averaging principle. So let we have this linear matrix Cauchy problem when right-hand sides and coefficients belong to this Lebesgue space L1. And then we have the next convergence. So at the beginning of the previous century, Tamarkin established this uniform convergence of the form 1 uniform. And then, Krasnoselsky and...
So what is K again?
K?
Is your no, what is K?
K, this one, the natural number. Some number.
And for what do you have it? Because F depends on it, or what? F and A depend on it?
It's yes, it's some parameter, and this is the systems of.
I mean, I understand T, right? The prime is with respect to T. That makes sense. But what is K? I don't get it.
K is some parameter in our systems.
Okay. Discrete.
Okay, because this in point, so you consider this convergence
there you use it, okay.
Yeah.
Sorry.
No, normal. So then Krasnoselsky and Crane, they gave more general conditions, and they consist in the next one, in the form 2, so in this convergence, when this is primitive, and in the existence of the integral majorant. So it's more general result. And then after that, this condition also was generate. So Levin reduced the last inequality to the next one when we have this one constant. And Levin understood that if condition 3 holds, so then condition 2 about integrate majorant, it's not only sufficiently, but also necessary for our conversion, this one. Okay, this is historical moments. And this results also cover the result of rate, in which instead of condition 2, we have this one in the sense of weak convergence. Also, these results were in somehow generalized by several mathematicians, Huan and others. it's concerning Cauchy problem. And when we move to general boundary conditions, so some difficulties arise. In what sense? That in this case, about our problems, like such types of problems, the solution cannot be unique or even do not exist. So, and Kiguradze for the first time investigate the sufficiently condition the solution the continuity with respect to the parameter this problem. So and this problem like called general problem and classical. So what means classical? They may contain Cauchy problem, mixed problem, integral problems, but they cannot contain the derivatives of the unknown function. And in future, I will talk that our problem may contain these derivatives. So let's briefly through. So Kiguradze had these conditions, general conditions, with these linear operators that act from this space to this space. And yes, what is BN? It's operators like this. Yes, systems of differential equations, ordinary. Yes, and this is like our operator that acts our unknown function. And this theorem actually inspired me to deal with continuity in a parameter. And this theorem says when our solutions is continuously depends with respect to the parameter. So suppose that a homogeneous boundary value problem, our generic in this point, has only trivial solution. This means that inhomogeneous has only one, and the following conditions satisfied. So we put some limitation on our operators and coefficients and some convergence, yes. And then for sufficiently large parameter, solutions of these problems unique, exist, and this converge fulfills. So this means that our solution, this y, it's our solution to problem, are continuous with respect to the parameter when n goes to infinity. So and all of this conditions are essential, but some of them can be deeply weakened. And this also was done by some mathematicians. And how it's work? They managed to realize that all of these results to systems of differential equations, so can consider it in with complex Lebesgue summable coefficients. And why actually we need to consider this, or why it's a little bit interesting? Because the methods of investigate all of these problems, generic and general, so they used in analysis of ordinary differential equations with distribution coefficients. Sometimes it's happened when physicists try to solve something, but they can't, and they ask the mathematicians, and then mathematicians help. It's like trick, but actually it's sometimes work. So in particular, when we talk about Schrödinger operators with potential containing Dirac delta measures, so and even its derivatives, and these operators with distribution in coefficients actively used in this question. When we have not only Dirac measures, even its derivative. So this is two monographs of Albevario and others that actively considered this question, and they have more than 1,000 references. So, and at the beginning of our century, mathematicians tried to do easy this task, and what actually they create. So the idea to consider these operators with distribution in coefficients was in the next one. So they defined such operators with distribution in coefficients and as quasi-differential with properly selected quasi-derivatives according to Shin-Settle. What actually it means? So let we have this formula differential expressions of the form 4. As you can see, Q belongs to this one space. And here we have Q prime. Even if we have here Q, it's will be like not good situation. But here we have Q prime. So, okay, let us consider that. Let us be given in a compact interval, and the function Q is understood in the sense of distributions. So Q belongs to this one, and Q prime then is signature measure on the compact interval AB. So the expression can be defined as Shin-Settle quasi-differential expressions with the following quasi-derivatives. How it works? We take this one y, yes, and define it like a zero derivative. And then y prime, like the first derivatives, was held to this one. So we need to take this Q in the best way when this product exists and belongs to L2. And when we do some this minus this, we lost this singularity. So everything is good. And then step by step, the next one we defined like was held to previously. And when this is Q like a good function smooth, so this definition of this Shin-Settle is equivalent to the classical one derivative. Okay, so we have this one, and now we consider the set of these expressions, and this Q epsilon, yes, and in the Hilbert space, each of these expressions generates a dense defined closed quasi-derivatives operators with the next domain. As you can see, this domain may contain any non-trivial function from like a continuous set. So this is actually bad situation. And this theorem gives... Capital Y is defined like this one.
You evaluate
Yeah.
the function.
Yeah, in the point this, and then this is first our on the interval AB we consider where is our control AB, yes, on the end. So, and this theorem give some result how we can avoid this difficulty when we have this y belongs to L2. So suppose that the resolvent set of the operator L0 is not empty, and these two conditions hold. Like we put some convergence, yes, and then in the sense of norm resolvent convergence, we have this one. So like each of the introduced operators is the limit of such operators with smooth coefficients. So that now we will move to the statement of my problem, and this is like when it's used and why actually we need it. So now we consider the generic problem. So firstly was Cauchy and the general, and now generic. It the most the most general conditions that also may contain derivatives of the unknown function, and the order of these derivatives is greater than the order of differential equations. So let we have AB, yes, interval, some parameters, and we consider this linear boundary value problem of the form 5 and 6. All matrix valued functions belongs to Sobolev space, complex vector C, and this operator. And there we have arbitrarily chosen. And this is our unknown function. Okay, the solution of equation 5 fill this space if the right-hand side like runs through this space. Actually, this is the theorem about homomorphism of these two spaces, and now we can say that our problem actually makes some sense. Then the condition 6 with this operator 7 is generic. So as I said, they may contain derivatives, in general even fractional, when the order greater than the order of differential equations. Okay, it's briefly say that complex Sobolev space is the set of n plus r minus 1 continuous differentiable functions on the interval AB. All of these functions and derivatives belong to absolutely continuous set, and the last one belongs to Lebesgue space LP. Okay, and now we associate with our problem for the easier to consider and prove our results, this operator, LB, that acts in this space. And actually, to prove that this operator is invertible, we need to introduce some matrix. We call this matrix like characteristic. Why we need actually this matrix? So we have some systems of differential equations with some strange or not good operators. And we don't have analytical representation of these operators. And to avoid this situation, we need to introduce this matrix, because to work with matrix, it's really easier than to work with some operators. So by this one, we denote the numerical matrix in which J's column is the result of the action of the operator B on J's column of this one. So we take this capital Y, and then step by step X on each column, and then we received this one. So block numerical matrix M of LB, this dimension of the form 9, is the characteristic matrix to our problem. So now we have this matrix, and we can say that the operator LB that corresponds to our systems of differential equations is invertible if and only if this matrix is non-degenerate. Actually, why we need this matrix? Because now we can solve some problem without parameter about indexes of operators to calculate some dimension of kernel and co-kernel. So it's really easier than to work with operator. And to formulate our main results about continuity in the parameter of solutions of our problem, we actually need to add this continuity parameter, yes, epsilon. And let us consider the same like previous, but without parameter. So all of the coefficients and vectors like in previous task. And this problem has the 0 index for every epsilon. And now, if we try to, in good way, to introduce some definition what we means under continuity in a parameter, everything will be fine. Okay, so definition 2. The solution to problem 1011 depends continuously in a parameter epsilon in this only point we consider if these two conditions hold. So there exists a positive number that for any epsilon and arbitrarily chosen right-hand sides, this problem has a unique solution. So it is the first that we needed. Unique solution from this Sobolev space. And the convergence of right-hand sides implies the convergence of our solutions. So in this meaning, we understand what means continuity in a parameter. And also, let us consider these three conditions. The homogeneous boundary value problem has only trivial solution. We now consider this one, yes, with parameter. This means that inhomogeneous has only one. In one Roman, we put some convergence on our coefficients, and this is to Roman means that we put some convergence, strong convergence, because we consider only strong. All our results do not guarantee uniform convergence in the Sobolev space. And we put some convergence on our operators. And this is the main results about continuity in a parameter. We say that the solution to problem 1011 depends continuously in this sense that unique, exist, and we have this convergence. In this point, if and only if our problem 1011 satisfies these conditions. So this is actually the analytical representation of our operator B.
So what happens if you change the boundary condition? That is condition 1. You have only one solution.
If I have only one in this one,
Yeah, if you have more than one, what happens?
what happens? But we need needed that our problem is well possedness. So it needs to has only trivial in this homogeneous case, because our operator is invertible. So and then if it's some lots of solutions, it's maybe not work. So, but it's need to think about it. Thank you. So this analytic representation, and when we have Sobolev space, when P is equal to infinity, like non-separable, we don't have this analytic representation, and we need to avoid some difficulties. It's only I show how it looks like. And we supplement our results with a two-sided estimate of the error and Weade's discrepancy of the solution. And we have this double inequality that say that the error and discrepancy of our solution have the same order of smallness. We only have some estimate in this one. So if our problem satisfies this condition, then this double inequality holds. Okay, and now like one of the example of this huge analytic theorem here, because multipoint boundary value problem is one of the example generic problem. It's also work if you consider only the equation the first order, and when you have a lots of derivatives, so like a one-dimensional case, and all of these results like works. So let us consider on the example a multipoint problem. So let us consider this one. So what means these three sums? When we have our it's maybe don't see, it's AB, our compact interval. And this sums means that we took these sums on the derivatives. It's okay. And this means that we divided our interval by some tj point. Yes, and we took the sums on these points, and the number of these points can change. And then we have some series of points, tjk, we call tjk, that goes to these limit points. So, and the number of these points in each series can also change. And this is one of example of our generic conditions. So, also we say that the solution to this problem continuous if it exists, is unique, and this converges holds. That's the meaning. And now we also, from our necessary and sufficiently condition, we have these results that say us that if our problem, multipoint, satisfies some assumptions, then the solutions are continuous with respect to the parameter. So, firstly, we divide it into case, because it's easier to prove when p is equal to infinity and when p is less to infinity, but the methods of proofs not the same, and they not cover. And we have some lots of conditions. We get this from our proving, so it's not really necessary. But we say that for this multipoint boundary value problem, we also have the sufficiently condition when our solutions are continuous. Yeah, of course. So we have this one results and this results in this case. And as I said, that do not guarantee uniform convergence. And the last one, this theorem concerning some approximation property, forgot everything that I said. So looks on this boundary value problem 1516. Okay. So, and on this sequence of multipoint boundary value problem. And we proved that for each of these problems, we can build explicitly some sequence of multipoint boundary value problems that such that the solution of this problem goes to the solution to this problem. So, and now we have some limit theorem how we can build really explicitly the conditions, the solutions of this problem, and this theorem say us about it. So this is some publications, and thank you so much for your survivor.
Any questions?
Yeah, it's like quasi derivatives. You want to?
Can you explain that maybe in some elementary way? So you said that you have to use them when you're using distributional coefficients.
Yeah.
Understand how.
This Q, yes, thanks for question. Actually, looks in this expression. When Q belongs to this one, it's not good because the derivative can be not good, so not smooth or derivative distribution. So in this we take this one, and how we can say about derivatives. So in this sense, in like quasi derivatives we defined, and then these derivatives exist. If this like smooth, everything is fine because it's a classical one derivative. But it's really hard, not trivial, to take these coefficients Q and Q prime. But it's possible.
I'm still confused. So you define V1, okay?
Yeah.
Multiplied by Q. Q is a function, it's not a distribution.
This one, bound Q, from this one.
It's also distribution, right?
Sorry, so the derivatives, the quasi-derivatives don't apply when Q is L2. Under what conditions do you use these
Actually, this condition, it's in the sense of resolvent. And so, what do you mean? What conditions? How we get it, or?
Well, on the side you have Q is in L2.
Yeah.
And then Q is in D. So, these are different function classes. But do you use the quasi-derivatives when Q is in D?
Actually, this one, but we say if this belongs to this one, then Q prime is signature measure. It's like one of example, and it's work also for this one and for this one.
Okay.
Thank you.
Any further questions? Do you have an example where you can use your theorem?
What actually theorem? What actually theorem about continuously dependence or?
One of the theorems?
Yeah, we have example in our preprint when we take only like differential equations of the first order, and not multipoint, but without one point, when you have one equation and a lots of conditions in the boundary conditions. And it's also work for this. It's look like a very simple example, but it's work.
Thank you again.
You're welcome.